So I came from Bulgaria, and actually I work, I and my colleagues work in Faculty of Dental Medicine of Medical University of Varna, Bulgaria. Our university is for last year, for the second time, it was ranked the first in Bulgaria for medical education. So actually this is joint work of my assistants. Actually, this is part of PhD thesis of my assistant, Natalina Panova. And you have already heard the title, Corrosion Failure in Biological Fluids of Laser Melted Surface of Stainless Steel. Dental materials in the oral cavity interact continuously with the physiological fluids and are subjected to both chemical and physical impacts. Saliva is a hypotonic solution containing bioactinate, fluoride, potassium, sodium, nitrogen compounds, and proteins. Its acidity varies between pH 5.2 to 7.8. Therefore, the corrosion resistance of the materials used for manufacturing of dental construction is of great importance for their durability. Austenite stainless steels were first used for manufacture of implants due to their high corrosion resistance and good mechanical properties. In recent years, different laser technologies have been widely implemented in the production of various types of implants. These technologies include laser cutting, selective laser melting, laser welding, and laser heat treatment. Application of these technologies leads to microstructural transformations in the treated surface layer, which can change the corrosion resistance and biomechanical properties. That's why our aim was to investigate the failure of laser melted surface of Aisi 321 steel under corrosion in two types of biological fluids, artificial saliva with different acidity and ringer solution. Here you can see the specimens. We use this steel with chemical composition, which is given in the table. And the initial specimens were prismatic with dimensions 10 to 32, 100 millimeters, and they were made by milling. One surface of each specimen was treated by continuous CO2 laser. Here you can see the parameters of laser treatment, and we use three different regimes for surface heat treatment, as laser processing was implemented via modes guaranteeing various melting depths of the surface layer. After the laser surface treatment, the sample surface was ground of 3 samples and ground and polish of the last one. The austenite steel corrosion was studied by electrochemical corrosion test at temperature 37 degrees Celsius in two biological fluids, artificial saliva and ringer solution. Here you can see the chemical composition of the corrosion medias. Since saliva acid levels in the oral cavity vary between 5.2 and till 7.8 pH, the electrochemical corrosion was investigated in two pH variants, 6.5 and 5.6, as acetic acid was used to lower the pH level. Here you can see the corrosion test according to ASTM standard, which was used. The electrochemical corrosion test was performed using this apparatus, potentiostat, Radelkis. And here you can see the schematic view of electrogalvanic corrosion test. Surface morphology and microstructure of all samples were investigated. Here you can see the conventional procedure for investigation for preparation of cross sections and for preparation of samples for investigating of microstructure in the depth of laser surface layer. We investigated all samples by optical microscopy and by scanning electron microscopy, as we investigated also changes of chemical composition by EDX detector of SEM microscopy. And now about the results before laser treatment. The plain stainless steel consists of two-phase microstructure, which was relatively inhomogeneous in terms of morphology and chemical composition. It consisted of austenite grains with grain sizes between 20 to 150 microns, banded delta ferrites here. This is delta ferrite, and this is also delta ferrite, and spherical carbides at the grain boundaries. After laser melting, two-phase microstructure consisted of delta ferrite and austenite into the dendrites. As these two phases are presented into the surface melted layers, as delta ferrite is situated between in the interdendrite spaces. The microstructure of laser melted layers is more homogeneous in terms of morphology and composition, as it can be seen here in this picture shown, taken by optical microscopy. Here you can see the surface morphology of the investigated steel after corrosion test. Regardless of the type of and acidity of the environment, two types of corrosion processes took place on the sample surface: pitting corrosion and crevice corrosion. Corrosion pittings of different shape and sizes were observed on the surface of all samples, as their number was higher in the laser melted layers. Here in these two pictures at left and right, you can see the SEM investigation of corrosion damage on the surface of the investigated steel before, pictures AB, and after laser melting in Ringer solution at left and in artificial saliva with high acidity at right. AB non-treated surfaces, and CD specimen 1, EF specimen 4, and JH specimen 6, and these are pittings on the surface of laser melted layers. As you can see, regardless of the corrosion media, nearly the same types of pitting are observed. In both corrosion media, the pittings on the untreated steel surface were characterized with irregular shape, smooth walls, and sizes between 10 to 300 microns. The pittings on the surface of the laser melted layers had rounded shape, sizes between 10 to 400 microns, less depth, and rough walls. And now about the development of corrosion in depth of the investigated steel in Ringen solution. The corrosion destruction of untreated steel surface was selective, mainly of delta ferrite in the form of pittings of irregular shape and great depth between 50 to 300 microns. Irregular corrosion was present at the austenite grains. Intergranular corrosion was presented at the austenite grains, here shown with these arrows, around the grain boundaries near the surface. Here you can see the SEM pictures of development of corrosion damage through the delta ferrite in the depth of untreated steel. The destruction of laser melted layers. The corrosion destruction of laser melted steel layers was selectively by delta ferrite destruction in the form of shallow with the sizes between 40 and 100 microns, equiexed pittings. As you can see on all of these pictures, all pits are very shallow with very rough surfaces. The main mechanism of corrosion destruction of the investigated austenite stainless steel with no surface treatment and after laser melting was identical: selective destruction of the corrosion non-resistant delta ferrite phase, shown here, in the form of pittings. The morphology and size of corrosion pitting was different, which was determined by the delta ferrite morphology in the microstructure. And as a conclusion, we can say that the mechanism of corrosion destruction in the laser melted layers consists of the following stages: destruction of the delta ferrite and network of austenite dendrites, as it is shown in picture B, fracture of the austenite dendrites and pitting formation, and round shape pitting with rough surfaces as a result. From the point of view of resistance to corrosion failure, laser surface melting of the investigated steel improves conditions for enhanced durability of the dental and implant constructions. Thank you very much for your attention. As you can see, this work was done with the help and funding of the European Union Next Generation project, with the resilience plan of the Republic of Bulgaria. Thank you very much for your attention.